So anyway, today I want to go ahead and take care of two other things and then work on the search form and the track form of the radar equation, because these are the two basic forms. The equation, again, I'm going to start by saying that when we have a radar, some of the key features are beam width, and the horizontal end and the vertical direction are azimuth and elevation. Now, this is really something when the beam is scanning, and it's basically a mechanically moving radar. This is true. This is typically what I'm going to talk about. It's called the antenna dwell time. And it's T antenna dwell. And that's really equal to, well, it's the amount of time the main beam is on a target. Now let me just show you what I mean by this. When you have an antenna like this, let's assume the antenna is rotating. So if this is the main beam and it looks like this, I'm not going to draw the side lobes, and we have the 3 dB beam widths right here. This would be theta 3 dB. Well, this is going to be rotating at a certain velocity, at a certain rate, I should say, omega. That would be in radians per second. Now the 3 dB beam width is from here to here. So if you assume this is the main beam of the antenna, if I want to see how long the beam itself is between the peak of the beam is between the 3 dB low and 3 dB high point, it would be rotating like this, and you want to know how much time, like literally my arm would spend in that 3 dB beam width. Well, you think about the fundamental equation. I know that omega times t is equal to an angle. Omega is in radians per second, t would be in seconds. That gives you an angle. What we want to know is how long of a time it spends in the 3 dB beam width when it's rotating. So this would become theta 3 dB would be equal to omega times t, and this would be the antenna dwell time. So that would be theta 3 dB divided by omega would be the antenna dwell time.
Is that a 3 theta 3 dB?
It's the 3 dB beam width. I just put theta 3 dB.
Okay, it looks like a greater than. So.
Let me try to do you justice. This one?
Yeah.
This is for the search form of the radar, right?
It's for, it doesn't matter.
Okay.
We're going to get there, but this is the antenna dwell time period.
Okay.
It doesn't matter what kind of radar it is, or how the radar is operating. Now, something to be said. Mechanical things move slowly compared to all the things that we talk about, the frequencies and rates of change, and for most radars in the electromagnetic domain. But that means that this is actually got a certain number of pulses, and I'm going to label this NP. This is going to be the number of pulses that times the actual T, and this would be the coherent processing interval. Now, remember before I told you that when we talk about radars, and in your reading you probably saw this, that in general, when we take a look at a radar, we're taking a look at something that's going to send a whole train of pulses as such. And we're going to have n pulses. This is going to be the pulse repetition interval, or T, and this is the period tau. And the coherent processing interval is really n times the actual t, or n times PRI, or it's equal to n divided by PRF. They're all one and the same, but that's how long, that's basically how much information you're going to send and then receive, and use that information for processing. That basically, we're going to take this pulse right here, we're going to flip it around and then move it through there in what's called a match filter operation, and we can actually get the range to the actual targets and the relative size of the targets by doing it. But this is the important thing. This is the coherent processing interval, and it's really the minimal amount of time you have to have the radar main beam pointed at a target. Now that should make sense there, but it's not just one pulse, it's a string of pulses. But there can be more than one coherent processing interval in an antenna dwell time. And that's okay, but it also means something. It means that you're slowing the rate that you actually can go through and search an area. Do you all follow this, class? So this is the antenna dwell time. That's important to understand. The dwell time itself, the dwell time is really the amount of time you stay on target, and it has to be at least one coherent processing interval for any kind of fidelity for the actual radar. That's the thing. But this is the antenna dwell. Remember before, the dwell time was just the amount of time you stayed on target, right? That was the fundamental difference. This is the antenna dwell, and they're used interchangeably sometimes. So, I have an example here. I'll just tell you that a lot of people have questions about the different nomenclature used, but this is a simple thing. If you have an example of this, it's in the book. If you have the 3 dB beam width equal to 3 degrees, that's about equal to 50 milliradians. It's about that, and if omega is equal to 90 degrees per second, I could put that in radians, but it would be pi over 2 radians per second. Then, if we want to take a look at the antenna dwell time for this one, it would be really 3 degrees divided by 90 degrees per second, or it would be 1 over 30 seconds. And that would be the antenna dwell time. Now, if you wanted to figure out how many coherent processing intervals there were in there, and this should be fairly straightforward. If I assume, for instance, that the PRF, pulse repetition frequency, is 10 kilohertz, and the number of pulses in a coherent processing interval is 32, and now I want to know the actual number of coherent processing intervals are in the one antenna dwell. Do you all follow me what I'm doing? I'm trying to figure out how many coherent processing intervals are going to be in an antenna dwell. Everybody got that? So this is straightforward. First thing I have to do is find out what the antenna dwell is, right? Well, that's it right here. That's the antenna dwell time. Now, the next thing I have to do is figure out what the pulse repetition interval is. Correct, class? With me? So if this is the pulse repetition frequency, the pulse repetition interval, or tau, is 1 over the pulse repetition frequency, and that's equal to 10 to the minus 4th seconds. That should be clear with you, right? This is straightforward. There's nothing tricky. Next thing I have to do is figure out what the length of time in a coherent processing interval is. And that's going to be that. It's going to be the PRI times the number of pulses in the coherent processing interval. That's 32. So it would be 32 times 10 to the minus 4th, or 3.2 milliseconds, and that should be clear to everybody. So now I know the number of pulses in a coherent processing interval would be the antenna dwell time divided by the actual time for the coherent processing interval. The antenna dwell time is 1 over 30, and then if I take that and divide it by 3.2 times 10 to the minus 3rd, I get really 10 to the 3rd over 30 times 3.2, and I can't tell you what that is exactly, but it's what, roughly, it's over 10. Can anybody just do that real quick?
10.4.
10.4?
That's 3.2 milliseconds up in the right. I can't make out what you're in.
Here, yes.
Yeah.
So it's 10.4. And that's just a simple example of a calculation where you have to use antenna dwell, the time involved with the time of it takes for a coherent processing interval, and you had to use initially the PRF to get that information. And that's a very simple example, but that way it should answer any natural questions you have about this. And in any kind of question I would give you, I would specify the number of pulses in the coherent processing interval clearly, and I would specify a mega if it was any kind of an antenna that's scanning, all right? Those are mechanical antennas generally. Now, I want to say one other thing too. Most radars, nautical radars, like if you look on any of these charter boats and stuff like this, they are revolving radars. They are not electronic paneled up there because it's very expensive to get a whole bunch of panels up there and do an electronic scan. They're just radars that rotate like this, and you have a basic screen. If you ever seen, anybody ever seen a radar screen, a typical CRT radar screen where they have a little bit? Well, now they have LCDs, and all you'll see is something effectively that's imitating the old legacy radars. And when there's clutter and stuff like this, there'll be something that indicates this, usually with a bright dot. And the brighter the dot, oftentimes they use color, like the darker the red, the larger the target, something like that. They'll have a way of, and you see this with, if you ever looked at weather radar, all right, the dark reds are usually the densest, or the ones that have the highest top clouds and stuff like this. Those are the things that indicate problems. They always use, usually they typically use red to indicate there's a problem. All right, now, after that, I'm going to get to the search form of the radar equation, and I'm going to put up a bunch of stuff so I can pull from it and show you how this stuff, how you actually assemble or design a radar. And he talks about this in the book. The big thing is this. And it's all trade-offs. Typically, the thing you want for radar is a very high gain antenna. The bigger the antenna, the greater the gain usually, and that means a bit more expense. And the second thing you want is a powerful power amplifier to transmit. These are the big costly things. The electronics involved, really the digital signal processing. I can't say this with authority for super high frequencies, but for most radars, that probably is an insignificant amount of the cost. Relatively insignificant. I mean, I don't know how much these microcontrollers cost these days. They're under $1,000. You can get a microcontroller that pretty much can do anything you want on most radars and program it right. Now, the displays and stuff like this, any additional processing to get rid of clutter and things like that, that might be more pricey. Anybody ever do any programming with microcontrollers, or Arduino? You do that, right? Now, a true microprocessor like an Intel unit, that's more expensive, but it's still minor compared to these power amplifiers and stuff like this that have things that are called power couplers, which can go hundreds, well, I won't say hundreds, at least $20,000, $30,000 for something that can put out a megawatt. It gets expensive. All right, now, back to the fundamental form of the radar range equation, right here. We know that it's always going to be signal-to-noise ratio, signal-to-noise ratio for n pulses. This is going to be n pulses, and that n is going to be associated with the coherent processing interval, by the way. All right. So you start with this, and you should be able to do this at least once by yourself. You usually fall into pitfalls. So you start with, it's actually transmitted power times gain of transmitter times gain of receiver. For this case, I'm going to assume monostatic, and I'm going to assume gain of transmitter is gain of receiver. So it's gain squared. Next thing you get out of here is times sigma. That's the radar cross-section, the size of the actual target. After that, now you're going to get lambda squared. This is on top. I think you remember this one, right? After that, you're going to get the number of pulses. Now this is divided by 4 pi cubed, r to the 4th, and that takes care basically of the power received. That's the power received right there in n pulses. Now you have to divide that by the noise power, which is going to be KTFB. All right, and that's K is going to be Boltzmann's constant, T is going to be in degrees Kelvin, F is, I call it a fudge factor, but it's a noise figure for the amplifiers involved. B is the bandwidth over which it's operational. And then I'm not gonna, they don't usually put this in there, but you can put in losses. This is gonna be also, the total losses for the atmosphere, the system, radar processing, you know, from anything that involves like quantization error. And that's the general form you always start with any kind of, anything that has to do with a proof for a certain type of antenna. Generally, there's two types. There's search and then there's track. But these can be used, you can do search while you're tracking targets. So in modern electronics, once they designate targets, they're going to be going back and forth to them every 10 times a second and see if they're moving and where they're moving. And they project the natural path, and then if they can't pick it up where it was, they'll look in the future where it's probably going, things like this. But we'll do some problems related to this. Now, here's where we start changing this for search. And I'm going to put some equations over here we'll keep going through. The first is something that you're familiar with. Do you all remember how antenna gain or directivity is equal to 4 pi, it's divided by the integral of the normalized power density times, then it has sine theta, d phi, and it was over all space. Do you all remember that from back in the day when you had EMAG 1 or 2, right? Now, here's what happens here. This gets approximated. We don't use this for gain, and generally speaking, this is equal to really, I should say this is really directivity, but let me just say this. I know directivity is approximately equal to gain if the efficiency of the antenna is about 100% or close to it. And that's typically the assumption, unless there's a reason to assume differently. Now, when we look at this, we can assume the gain or the directivity is about equal to 4 pi. This is something new, please pay attention to this. Now what you can say is this entire integral is approximately, for high gain antennas, approximately equal to the actual beam width in the theta and beam width in the phi direction. This is going to be the 3 dB beam width. It's approximately that. That's all that normalized power integrated is for a high gain antenna. It's really just the main beam widths multiplied together. And they have to be in radians, by the way. All right, this is radians, 4 pi ster radians in a complete surface of a sphere. All right, now if I have that, that's one of the things I'm going to use. The next thing is, I know that lambda squared over 4 pi, oops, Marcus, I'm sorry. Here, no, go ahead, keep it plugged in. What I'll do is work over here. I know that lambda squared over 4 pi times the actual gain is equal to the aperture. Search radars use aperture, and I'm going to use it A sub B. Matter of fact, let's go A sub P on this one. I've seen it both ways. So that means gain is actually 4 pi over lambda squared times the aperture of the antenna. That's the next thing I do.
4 pi?
Lambda squared over 4 pi times gain is aperture, right? Do you all remember this class? Right? I mean, this one we had in EMAG 2. Most people probably use this over and over and over again. Use it for what? Radar, use it for freeze transmission, use it for just about everything, right? Anything that has to do with antenna, you're always talking about both gain and aperture interchangeably, and they're proportional to one another. Now, because I said this gain was approximately that, I said it's 4 pi over 3 dB times phi 3 dB. One thing I can say is, therefore, the actual aperture of the antenna is equal to lambda squared over the 3 dB beam width. That's one we're going to use. That's one we're going to use. You all agree with me there? The next thing is this. I know that the average power is actually equal to the peak power, or P transmit, we'll assume that's P, times tau over T. That I know for a fact, right? You're just taking the duty cycle by the peak power and getting the average power. Average power is used for search radar equation almost extensive, from what I can tell at least, exclusively in the design, not peak power. Yeah?
There's a Q in the book, and you didn't really talk about it before.
Well, here's what he says in the book. He says that Q is just the intensity, where you take transmitted power over 4 pi r squared, if that's what you're talking about.
Right.
All right, that is just the power density from an isotropic source on target. If you take Q times the actual gain, now you've got the average power density. All right, but this is almost an irrelevant step, because we know we're gonna be talking about antennas with gains. Do you follow me, everyone? Did you all remember seeing this thing, Q in the book?
So we're not using Q at all?
Well, in a sense, we are, because we multiply Q by gain to get our average power density. So, in fact, yes, we're using, but not calculating it. Does that make sense? It's the whole idea is when you're talking about antennas and anything related to electromagnetic propagation, power falls off and the far field is 1 over r squared. That's the real thing they're saying. That's all they're saying. So that means from this equation, I can get that the actual power transmitted is equal to tau over T times the average power. And this one we'll use 2. Agree? These are things we're going to be using in that equation. And this is the way I suggest you do this. If you're asked to do a proof or create something, an equation that has these variables, write down the equations on a separate sheet or somewhere so you can just pull from them. You'll see it get messed up if you don't.
So the T is PRI, right?
Yeah, and I could put PRI. I prefer T because you're very familiar with that as a period, I think. More familiar than that than PRI. PRI is usually an expression used in the radar literature. But see, the T is used for so many things. There's a T for dwell time, T for antenna dwell, T associated with a coherent processing. T is used for about everything. And the large T, small t designations in some of the journals kind of gets blurred. So that's why they often talk about the actual pulse repetition interval, pulse repetition frequency. Those are unique designations. Just remember that. Now, when I have this right here, I could say that's also transmitted power would be tau times PRF times PAV. And we can keep going on with different permutations. Now this one's important. They use antenna dwell a lot and the actual T of the coherent processing interval. So when I take a look at first the search space, I'm gonna put it up here. In case, does anybody have you got your books yet or not? You got okay, you got a book. How many have a book in here? Has anybody had any trouble getting a book? I don't have to order anything, which is good. I'll tell you where I'm pulling from, where I'm going with this. We're going to do a little signal processing, hopefully today too. This is in chapter 3. The first 2 chapters are basically, in my opinion, old hat to you guys.
I got a quick question about those last equations you put up there.
Yeah.
If P average is the transmitted power times pretty much the duty cycle, wouldn't the transmitted power be PRI
You know
over
what I did?
tau?
This should be capital T. That's my bad. I made a mistake. This should be capital T divided by tau. Yeah, this is a number greater than 1, not less than 1. My bad. That's absolutely true. No, I mean, you can figure it out from there. Is there a wastebasket anywhere?
There's one.
I wish they would put it in the back. You know why it's there? Because the janitor just drops it there after he gets it from the truck.
Right, so then,
All right.
so is PT wrong underneath it, the tau times PRF?
Yeah. This should be, PAV. That's it. Okay. Next, the next thing I want to say is, if this is the search space, remember that's gonna be theta 3 dB, that's the actual azimuth. The elevation would be phi 3 dB. This is designated as omega, and omega here is equal to phi 3 dB times theta 3 dB. And it is in radians almost exclusively. You can do it in degrees, but if you do this in degrees, everything else has to be in degrees, like the beam width and everything like that. So just make sure if you're gonna use degrees, you have to use it for everything. All right, and now that I have that, I'm gonna put up one more equation, maybe two. I know that n times the actual period is equal to the time involved with the coherent processing interval right there. And I also know that n, and I'll call this dwell times T CPI is the antenna dwell time. Now, the reason I'm doing that is because there's several things that I'm gonna reference. Where this antenna dwell is going to be important. Now just realize all this we've covered, but I'm putting it up there to draw from it. All right? Now, when we have this, we know that basically we're going to chop this up into a bunch of pixels. And then we're going to figure out how long it takes to scan this region. So each one of these has a width. This is theta 3, oh, I shouldn't put 3 dB here. That's really theta and phi total. This is the total extent of the image. This is gonna be theta 3 dB, and this is phi 3 dB here. This is just one division. Y'all know what I'm talking about here? So the total number of pixels here, M, would be the search space, total search space, divided by, and it would be phi 3 dB times theta, or I should say theta times phi 3 dB, the beam width. And that's the total number of positions, for lack of a better term. Now I want to get into this using the antenna dwell time. This is I guess the way he does it. And he's assuming worst case scenario, it's a mechanical antenna. So how long does it take to scan this region? Well, if you have to stay in each one of these pixels for an antenna dwell time, the total time, and this is called the frame scan time, would be equal to m times the antenna dwell, and that should make sense to you. That's the frame scan time, right? If you want to, I can put down frame scan. Now, that antenna dwell is here. That's equal to m times, well, I'll tell you, I'm gonna leave it like that. We'll do the interchanging in a second. So the antenna dwell was
So omega is just the number of squares, right?
no, omega is going to be the size and rate. It's radians, or
Okay.
it's
Yeah.
actually square radians. And this is the size of this thing. So if I look at the amount of time it takes to get through there, the frame scan time, that would be omega divided by theta 3 dB times phi 3 dB. That's replacing m. And then it's times T antenna dwell. And if you want to go backwards, you could say the antenna dwell time is equal to right here times the actual frame Either one's acceptable. And they're both the same. And now, trying to find what this equation is in the books, I can tell you where the reference is.
By those equations, would M always be 1?
What?
Because up at the top of the grid, you have omega designated as.
These are 3dB beam widths. This is the entire domain.
Yeah, I think he's talking about above that chart, you put omega equals.
That's wrong.
A-
Thank you.
That's why I was asking the same question earlier. but-
That's wrong. I'm sorry about that.
Okay.
That's the extent of the region. We'll do some problems with this, but it's the size of the region. This might be, it could be like pi over 2 radians or 90 degrees, and this might be 30 degrees, something like that. All right, so that would be pi over 6. So it would be pi over 6 times pi over 2 would be the total in radians squared. And then you would divide that by the beam width to get the number of spaces. The beam width. I'm very sorry about that. I have that. Then, let's see here. I think I've got all that right. Now I need to give you the equation that we're going after.
So we just assume the size of the target is not large enough to really matter at the scale of what we're talking about? Like, the target's not so large that it's going to be covering a substantial portion of our beam width?
Oh, the target's inside of it. I mean, that's actually an interesting question. What happens if the target's so close that you get eclipsing where it's several pixels? And that can happen. Here's where that happens in weather radars. They'll see a massive storm front. And as they're scanning the targets in everyone, and literally the sigma value is a variable of the pixel number, but it's in every one, if that makes sense. Oh, weather radars are search radars. They're not track radars. But the real thing that they do is, as far as I understand, they really try to present the density of the rain field or graupel field or hail field. And they do that with some kind of color marking system usually. How they get that is because at a given range, they know the relative return from any clutter, all right, that's out there. They're gonna get some from trees or anything in blue sky. Now, anything else out there that you're getting return from starts scaling up. Any power level that's beyond that as it gets higher and higher, and that's where the color starts shifting to. And it's not a linear scale, it's logarithmic, but if you see these dark reds, that means you've got a very large, I guess, rain field or hail or graupel field. And we could spend some time talking about that, but not right now, it comes later. So the form I'm gonna go for right now, that's used a lot, is it's on page 80, and it's equation 2.43. So here's what I'm gonna do with this. I wanna just get there because you're gonna be doing things in the future where you're gonna take all these equations and keep on modifying or adjusting the fundamental radar range equation to get the information you need. So the first thing I'm gonna do, and you don't need to write this down if you don't want to, just watch. First thing I'm gonna do is this, that's why I'm gonna erase it. I'm gonna say that the transmitted power here, I wanna replace it with average power. So transmitted power is average power times capital T over tau. So this becomes P-Av times capital T over tau. I've just replaced one term. Y'all follow me? The next thing I'm going to do is take the bandwidth. And I know bandwidth is, I didn't put that there, but bandwidth is 1 over tau. It's approximately 1 over tau. So now I take bandwidth here, and I have tau. All right? You all with me? Now you can see the first thing I can get rid of is this tau right here. So now I've got rid of it. Agreed, class? Next thing I can take a look at is the gain squared. Now gain, right here, is 4 pi lambda squared times the aperture, or 4 pi times the 3 dB beam width, divided by the 3 dB beam width. And his book, let's see if he has used beam width, or he stays with aperture here, so that's okay, and he uses a sub E. I had a P here, but I can use an E. So now I'm gonna replace this gain, right here, and I'm gonna square it, and the gain is gonna be 4 pi times the aperture over lambda squared. Square that times the aperture squared. You with me? What?
The book just, for beam width, it approximates theta bandwidth as 70 times lambda over D.
For what antenna?
It doesn't
It's
say
a wire
specific,
antenna,
but-
it's a wire, but don't, I mean, wait, no, that's a circular dish. We'll get to those
Okay,
approximations.
yeah.
I just wanna say one thing, all right, when you're dealing with parabolic dishes or circular apertures in general, like, just a circular patch antenna, there are formulas for beam width that are fundamental and known by everybody. Same thing for like far field from a long wire antenna, it's lambda over 2 pi. These are formulas that they'll use and reference all the time, but you don't worry about them. Things you need to become second nature. So now the next thing I'm gonna do is this, if you all watch this for a second. I like to do this just once, just so everybody understands how you go about it. See, there's a 4 pi cubed and a 4 pi squared there, right? So I'm gonna get rid of this and get rid of that totally. All right. Now, the next thing I'm gonna do is you see how that lambda squared and one of those lambda squareds will cancel. You all see that, class? It's lambda squared that's divided by lambda to the 4. So I get rid of this and I get rid of the squaring option, and then I put lambda squared downstairs. And I put it right here at the end. And I'm gonna put my aperture squared right here. And T. All right. Now, the next thing I'm gonna do is I have T times N.
You have a T on both.
Huh?
You have a T above and below.
This is temperature though. This is time. This is PRI. That's another
right.
reason you should use PRI probably, but I'm gonna leave it as T if you don't mind. All right. This is gonna be the temperature, and I apologize for not putting a degree symbol or something. It's degrees Kelvin. So now with this times this is the coherent processing time, so. And I've got that. And then the next thing I need to do is get rid of this aperture and get the actual frame search. So the frame search is going to be, let's see here. That's the antenna dwell divided by, hold on for a second.
The book gets rid of this aperture by relating it to gain through gain is equal to 4 pi aperture over lambda squared.
I know, we did that already. We got rid of gain squared and replaced
Okay.
that. All right, if you look at, I'm gonna put this formula up and I'll show you, we're gonna get there in a second, but I wanna put it in terms of his variables, and he has this. SNR for N pulses will be equal to the product of PM times the aperture, so we'll break that out by itself. And then it's times 1 over 4 pi KT, and that's in degrees, we'll call it T0, times F times LS. Then it's gonna be sigma over R to the 4th. That breaks out by itself. And the frame search time divided by the actual size of the region. That's where we wanna go, and we can get there, I think, fairly straightforward, because next I'm gonna have PM by area by itself. So what I'm gonna do is multiply this by area, you have the antenna, and leave this by itself, just as one. So now we have this part. Now the next part I'm gonna do, break out 4 pi k, T0, F, and LS by itself. So I have 4 pi. I have the 4 pi KTFLS right there. Right? This part of the fourth is still there. Now, I'm gonna go ahead and break out the sigma and r to the fourth. So I'll do this. And then I need I get the frame search in omega, and I'm left with all this. So I have area of the antenna times the actual time for the coherent processing interval divided by lambda squared. And I want to set it equal to frame search over omega. And here's how we're going to do that. I know that this aperture times the coherent processing interval, I'm going to just erase this right here. When I look at the area times T coherent processing interval and divided by lambda squared. Now, this is what you were saying. I can replace that by lambda squared over 4 pi times the gain. And the gain is really going to be the 3 dB. Alright, so that's replacing this by lambda squared over 4 pi times, oh, sorry.
Okay, yeah.
I did that wrong. Let me do that right. First, gain is equal to lambda squared over 4 pi times the aperture. And gain is also 4 pi.
No, that's not. It's
Oh, I'm sorry.
Yeah,
Yeah,
it's
that was
5
gain. I'm bad about that, sorry. That's the aperture.
Yeah, that works.
Now, getting back to this. I can replace gain by 4 pi divided by 3 dB. And I'm just gonna put theta 3 dB there, which gets rid of the 4 pi. That's where I'm going with this. So I have that as the aperture. Now, if I take that, I can see and replace it here. Now I have lambda squared over phi 3 dB, theta 3 dB, and then it's times T coherent processing interval divided by lambda squared. So the lambda squareds cancel. And now I need frame search over omega. Let's see here. I know that this
If you multiply that by omega, then you'll get time of frame search.
pardon me?
If you multiply that by omega and the in AD, then you'll have the T of frame search.
Well, wait a second. I mean, this is the only thing I'm trying to get frame search over omega, right? In terms of these things, and I know that's gonna equate to it, but you're saying multiply this by omega?
Yes, because
All
essentially,
right, if I multiply top and bottom by omega, right?
or big omega, capital.
Oh, I see, just, both by capital omega, right? Go ahead.
It would be, what is it? One, say, top
But
and
see,
bottom.
this has to be multiplied by the intended dwell time, which is gonna be NP times this, right?
Mhm.
All right, so if you multiply NP here, NP, now I do have the intended dwell time.
Mhm.
All right, you can do that. Let's see what happens. So NP times that is gonna be T intended dwell. And then, now it's times, and I still have omega over omega here. I have NP here, and then I have phi 3 dB, theta 3 dB. But that's interesting because this right here, divided by these two, is the intended dwell time, isn't it?
That would be
No, it's the
M.
If I take a look at, oh, wait a second.
frame
no,
search is
omega.
equal to antenna dwell
Sorry,
time
sorry.
times.
That's the number M, my bad. You're right, it's M. So this would be M, I can just put M here. And now,
And then the left side turns into TFS because that states the equation for it.
this is gonna be TFS right here, right? That's the frame search. And that's fine, but now we need omega downstairs, and we got an NP somehow left over. And I think what they did is assume that the intended dwell time had one coherent processing interval. That's my, because otherwise you're gonna get this stuck here. I'm almost positive that happens. But needless to say, when, this is one form of the search equation, and I'm gonna make a note here. It's assuming the intended dwell time is the time for the coherent processing interval, I believe in this assumption. The way they did this, yep.
Is it? Like, should we take the book's advice or your advice?
For what?
Is that true? Oh,
This equation, generally true, I can tell you this one's used by everybody.
okay.
All right, for a search, this is basically designing a search radar, and now I'm gonna talk just a bit about this. This is the search form of the radar equation. Radar range equation. I have to do this one time, and I'm sorry I didn't go through this in a smoother way, but I gotta tell you, this is the critical thing. When you're designing a search radar, usually what they do is separate variables into things you can actually design for and things you can't design for, all right? For instance, the target size is something you have no control over, all right? You just can't. You can't also, you have no control over really the losses to a large extent, atmospheric losses. The temperature of operation is almost always a constant, stuff like this. So this term is usually broken out by itself. That's the reason they chopped it like this. This is something you have no control over. However, this is the thing you can control. And it's the product of average power times aperture. Those are things you design for with an antenna, with the actual radar. You can control the amount of power, average power. You can control the amount of area. So in the book, what he does, and go ahead.
They break out the temperature and the noise factor and LS all on.
They're gonna have, they'll take, they divide average power in, an area by the LS, T0, and F. And I'll tell you why. Those are all things that are involving electronics to a large extent. You can use, helium to get cryo cooling and to really lower the temperature of the amplifiers. That's usually not done. That, as far as I know, most modern radars, with the exception of deep space, there's people that are doing astronomy and astrophysics do use the really helium-cooled amplifiers, but those are the only group of people I've ever heard of. Military radios, navigational radars, anything like that are almost always at room temperature. Or at best, slightly above that. But this is equation, go ahead. Oh. This is equation 244. Now, you'll notice that the signal to noise ratio, the 4 pi, okay, maybe if I can put this down here so I guess everybody doesn't have their books here, so I'll put this down right here. I'm gonna erase all that. What he's gonna have is the average power times the actual, the aperture of the antenna. And he'll divide this by K times T0 times F, and then times LS. Does he put the 4 pi here too, or leave it on the other side?
Other side.
All right.
He also doesn't put K over there, so you cannot control.
That's,
both.
you know, that's one of those things, I guess you could put K on either side, but it would make sense to go next to T0 because they're usually associated. It's usually KT, F, right, and bandwidth LS. But we can do it this way. This is on one side. On the other side, this has to be greater than or equal to, it'll be the signal to noise ratio. Now you'll notice he doesn't have a number pulse in there. It's assuming it's for all pulses. That are used, in other words, he assumes that the number of pulses in a coherent processing interval is indicated in the development of this. Then he's going to have times the 4 pi k, which is kind of interesting. Then he's going to have sigma over r to the 4th.
Other way.
I'm sorry, r to the 4th over sigma. That's right, it's inverted.
Cap omega over TFS.
And this is going to be the only comment I have. This is 2.44. All these things are things you design, you have control over fundamentally, even though I go as far as to say T0 and LS are usually things you really don't have that control over, but you do have the average power times the area. And for search radars, it's the aperture times average power is the key indication of how the goodness of a radar, for lack of a better term. It's a figure of merit. Whenever you see radars that are used for search, you'll see those two terms used multiplied together. And if you think about it, average power is in watts, and aperture is in meters squared. So it's watts meters squared are the units of that, and you'll see this. And that's an indication of the goodness, for lack of a better word, of the radar, search radar. And you know how everything has a figure of merit, right? When you talk about gain, that's a figure of merit of how well a antenna can focus its energy. Aperture in the same way, how well it can catch energy, for lack of a better term. But you have to get familiar with that terminology. Now the track form of the radar, I'm not going to have time to get into all of it. Track form of the radar has a couple of things in it. In his, the way he does this, that I got to just mention. I didn't have time to go through some of this that talks about, he's going to have fudge factors in here that are K sub M. I'll put it up in a second, but I got to tell you this, he's also going to make some assumptions for beam widths for different types of antennas, and he'll have something called tracking noise estimate, a sigma sub theta. All these things we get to in the future chapters. He just throws them out there one time to let you see it all. So the track form of the radar equation is really equation 254, and he does things where it has a rate of update. I'm going to have to talk about that a little bit later. I'm going to tell you one other thing about this track form that he puts out here. There's a lot of stuff he throws in, information he throws in here that is not well defined or described. This comes later in the chapters where we talk about real radars. For instance, I'll tell you this. you know the term root mean squared, RMS, right? You're familiar with it in terms of the RMS power associated, or I should say, RMS voltage associated with any voltage waveform, right? And what it means is you take the voltage as a function of time and square it, right? And then you integrate that over a period and then take the square root of that to get the RMS of the voltage, right? Well, there's things that are called the RMS surface roughness, where they literally take something that's a measurement of the height from some base, that they call it usually 0, and they'll take the RMS height of a region in 2 dimensions over a certain feature size, all right? That's useful for calculating backscatter cross-section. Tracking noise, error, and things like this are related to that type of information that's integrated in system processing, and it gets a little complex, and that's the reason I don't go into all the specifics of these equations right here. It comes later. But I will tell you one thing, that the update rate of a track radar becomes important, and we're going to talk about a couple of problems related to this. I have time today. Now we'll get to this statistical stuff in a bit. I wanted to do problem 1 and 2 if possible, and then I'll give you a quiz, because we've got 15 minutes, right?
The 13.
Let me just do problem 1, all right? All right, Alec, go ahead, give me the
This is from Feldman.
chapter 3, problem 1.
Oh, tell me you're ready.
Go ahead.
Determine the single pulse received power level from a target for a radar system with a transmitted power of 100 kilowatts peak. Oh, I'm in chapter 2.
3.
Oh, we were in chapter 2.
For a mechanically scanned antenna having an azimuth beam width of 2 degrees and an elevation beam width of 3 degrees, how many beam
2 degrees, 3, go ahead.
Yep. How many beam positions are required to serve the volume defined by a 90-degree azimuth sector and a 6-degree elevation sector?
So this is 90, and this is, how many?
6.
6 degrees. All right. Now, here's the danger. When we take a look at this, we want to figure out how many segments we have this way, running this way. So we take a look at the azimuth scan is 2 degrees, right? All right, so that would be 45 this way. Correct? It would be 90 over 2 is 45. Now, what about the vertical direction?
It's 2.
Here we have 2 degrees. Wait, is that right? It's is azimuth?
Yes.
Azimuth is 3 degrees beam width or 2?
2. Elevation is 3.
And it's 6-degree elevation?
Yep.
All right, well, then this is pretty straightforward. That means the number of beam positions, M, would just be 2 times 45, or 90. Go ahead, or 90 beam positions. Go ahead.
That's the whole question.
That's it?
Yeah.
Almost in.
Next question?
2. So I give you 2. If the antenna were raster scanning at 180 degrees per second, i.e. it is scanning in azimuth at 180 degrees per second, what is the maximum dwell time for each beam position?
All right. Now, your omega is equal to, what was it again?
180 degrees a second, so pi over 2.
180 degrees per second, right? And they want to know the time spent on each one of these beam positions. What?
What number is this?
3.2.
2.
3.2?
You know, I'm gonna get bogged down in this one. I'm gonna have to give you a quiz now, or you won't have a full 10 minutes. All right, so go ahead and, I just put everything away, it's a problem, except your calculator.
What are the rules of the quizzes usually? You said we get, since we get both quizzes, we get nothing, right?
You get nothing, just like the CME system, except calculator, you get a calculator here. And they're very simple problems. If you have a question, please ask. If you need, I mean, I supplied Boltzmann's constant here. I don't expect people to memorize that. You'll become second nature in a bit. And on Thursdays, when these lectures really start taking off, because then we get into a lot more theory. Could you please make sure you put your name on it? First, I haven't had problems with small classes, but I have large classes. Where people didn't make it illegible, or it would be something where they forget their name entirely. You can write down, assume that it's 290 degrees Kelvin. All right, it's room temperature, 290. And one other thing, since there's really no partial credit on this one, I double check your calculations. Just run them twice.
Is question E supposed to be the average power received back at the radar? And not the
Say that again?
Question E asks for the average power received back at the target?
At the radar.
Okay,
Should be a radar.
yeah, that's what I figured.
For F, he wants to convert to dB.
What?
For, part F.
Signal and noise?
Yeah, signal and noise.
You can put it in both, how's that? That one, it doesn't matter.
Was there a temperature we're supposed to use, or is that supposed to be?
290.
290?
290 Kelvin. Oh yeah, make sure you put your answers in the spaces provided.
Number of pulses is just one, right?
Yeah. There's nothing there but a coherent processing interval, so it's SNR for one.
You said that T is 270 or 290?
290. It's Kelvin.
Right.
What are you assuming if there's no credit?
Hmm?
Are you assuming we're using 300,000 or I use
For what?
299 for the
For
speed of
single?
light?
Well, use 3 times 10 to the 8th. It's common.
Okay, well, I use the other one, so my numbers are gonna be different than yours.
Not by much. I'm basically being the noise.
Okay.
That's good. well, it's 10:56, but it should be,
I don't remember anything.
Do that one more time.
do you want to put the answers here, Marcus?
I don't remember any of it.
Did you have a chance to do that?
I started doing the first homework.
This isn't really hard, Marcus, just keep up with it.
It's just a lot of memorization. I didn't program it into my calculator before, so.
If you